Hello students, welcome back to Chemistry Online Coaching. In this presentation, you will learn about the haloform reaction, its mechanism, and its applications in organic synthesis. This lecture is useful for all competitive and academic exams from high school to university level. I am Aditya Vardhan from adichemistry.com, Warangal. Before we move on to the topic, I would like to inform you that practice questions along with the answer key will be provided to help you practice and revise. If you are interested, please write your answers to the questions given in this presentation in the comments section and also send an email to adikemadi@gmail.com. Now let us start by understanding what is the haloform reaction, beginning with the case of a methyl ketone. In a haloform reaction, a methyl ketone is treated with excess of halogen such as chlorine, bromine, or iodine in the presence of a strong base, followed by acidic workup to give a carboxylic acid and a haloform. The carboxylic acid formed contains one carbon less than the starting methyl ketone. Overall, the reaction involves cleavage of the CC bond between the carbonyl carbon and the methyl carbon. This reaction finds application in the organic synthesis when a carboxylic acid with one less carbon than the corresponding ketone is required. The haloform reaction works with all halogens except fluorine. Fluorine is not used in the haloform reaction due to its high reactivity, which leads to uncontrolled fluorination instead of expected haloform reaction. Let us now discuss the mechanism of the haloform reaction. The methyl ketone contains 3 acidic alpha hydrogens as shown on the screen. Initially, one of the acidic alpha hydrogens is abstracted by the strong base, the hydroxide ion, leading to the formation of an enolate ion. This enolate ion is resonance stabilized. The enolate ion is a good nucleophile and attacks the halogen molecule, resulting in the formation of a monohalo ketone. During this step, a CX bond is formed. Overall, one alpha hydrogen of the methyl ketone is replaced by a halogen atom. The alpha hydrogens on a monohalogenated methyl ketone become even more acidic due to the electronegative halogen on the alpha carbon, which stabilizes, resulting enolate ion. Consequently, the reaction proceeds even faster, continuing until all the alpha hydrogens are replaced by halogen atoms, ultimately yielding a trihalogenated methyl ketone. The trihalomethyl group in the resulting ketone is a good leaving group. In the presence of a base such as hydroxide ion, which attacks the carbonyl carbon, the next step involves elimination of the CH3- group and formation of a carboxylic acid. The CH3- ion, being a strong base, then abstracts a proton from the carboxylic acid to produce the haloform CHX₃ along with the carboxylate ion. Finally, acidic workup will restore the carboxylic acid. Therefore, the balanced equation can be written as shown. For 1 mole of a methyl ketone, 3 moles of halogen and 4 moles of hydroxide ions are consumed to produce 1 mole of haloform, 3 moles of halide ions, 3 moles of water molecules, and 1 mole of carboxylate ion. Not only the methyl ketones, but also secondary alcohols containing a methyl group adjacent to the alcoholic carbon undergo this reaction. The alcoholic substrates are first oxidized to the corresponding carbonyl compounds before undergoing the haloform reaction. This oxidation step requires 1 additional mole of halogen as well as 1 additional mole of hydroxide ion. Apart from the compounds discussed so far, 2 other compounds also undergo the haloform reaction. These are ethyl alcohol and acetaldehyde. Ethyl alcohol is the only primary alcohol that shows the haloform reaction, as it is first oxidized to acetaldehyde under the reaction conditions. Acetaldehyde, being an aldehyde that already contains the methyl carbonyl group, directly undergoes the haloform reaction. Let us look at the physical states of different haloforms. Fluoroform CHX₃ is a colorless gas. However, remember that it is not formed in the haloform reaction, since fluorine is highly reactive and cannot be used in the haloform reaction. Both chloroform and bromoform are colorless liquids with a sweet smell. Iodoform CHI3 is a yellow crystalline solid with a characteristic antiseptic odor. Now let us go through a few examples. The first example is the haloform reaction of acetone, which is a methyl ketone. When acetone is treated with an excess of iodine and a strong base potassium hydroxide, followed by acidic workup, acetic acid and iodoform CHI3 are formed. You can clearly see that the carboxylic acid product contains 1 carbon fewer than acetone. Now the question arises, why is only 1 methyl group adjacent to the carbonyl group halogenated? In principle, both methyl groups could undergo halogenation, but only 1 methyl group is undergoing halogenation to give 1 mole of iodoform. You are now encouraged to initiate the discussion by posting your point of view in the comment section. The hint has already been provided during the discussion of mechanism. In this second example, methyl cyclohexyl ketone, another methyl ketone, is treated with excess of bromine in presence of strong base sodium hydroxide, followed by acidic workup, will give cyclohexane carboxylic acid and bromoform CHBr3. In this reaction, methyl phenyl carbinol, a secondary alcohol with a methyl group adjacent to the alcoholic carbon, is treated with excess of chlorine and strong base sodium hydroxide, followed by acidic workup, will give benzoic acid and chloroform CHCl3. Now test your understanding by solving a few problems. Don't forget to write your responses in the comment section. This is problem 1. You have to choose the incorrect statement about haloform reaction. Option A. A carboxylic acid with one carbon less than the corresponding methyl ketone is formed. Option B. Fluorine cannot be used in haloform reaction. Option C. Tertiary alcohols do not show haloform reaction. Option D. 2 moles of halogen are consumed when methyl ketones undergo haloform reaction. This is second problem. Iodoform test is not given by. You have to choose the correct option. Option A. 3-pentanone. Option B. Ethanol. Option C. Acetone. Option D. 2-pentanone. This is problem 3. You have to choose the correct reagent to achieve the following conversion. So option A, chlorine plus sodium hydroxide. Option B, iodine plus sodium hydroxide. Option C, both A and B can be used. Option D, none of the above. Once again, I am reminding you to write the responses to the above questions in the comments section and then send an email to adikemadi@gmail.com to get the worksheets with practice questions. That's all for now. Visit adichemistry.com for more information on this topic or search for Haloform Adichemistry on Google. Don't forget to like, share, and subscribe.